Welcome to All Wired Up, where you dive into exciting topics around tech, innovation, AI, and the future of digital life. Strap in, subscribe, and enjoy the journey.
Welcome to All Wired Up. Today we're diving into vector databases explained in 10 minutes. Have you ever wondered how AI seems to understand what you're saying, or why sometimes it gives you generic, unsatisfying answers? It all comes down to memory. Not human memory, but a very specific, mathematical way for AI to store and retrieve information with meaning. Today, we're going to demystify how AI remembers things using a powerful concept called vectors, or embeddings. This understanding is absolutely crucial for building the next generation of intelligent AI applications, enabling them to move beyond simple keyword matching to true comprehension. In fact, major players like Pinecone, Weaviate, and even MongoDB are investing millions into this very idea. Traditional AI often treats words and concepts as discrete, unrelated items. Imagine trying to teach a computer about cats simply by feeding it every article, image, and video mentioning the exact word cat. When you then ask it something about felines, it might struggle because it only knows the exact string of characters cat. It lacks the deeper context and understanding that feline is a related concept. This is precisely why chatbots can sometimes give you frustratingly generic responses, or even hallucinate incorrect information, because they don't have enough relevant, meaningful context to draw upon. They forget what they just learned or never truly connected the dots. So how do we give AI a better memory? A way to truly understand meaning and connect concepts? The answer lies in vectors, also known as embeddings. Think of a vector as a set of coordinates on an incredibly detailed, multi-dimensional map. Instead of a simple street address, these coordinates represent a concept's meaning in a vast, conceptual space. For example, on a simple 2D map, New York and Los Angeles are far apart, while Times Square and Central Park are very close. In our AI's meaning map, concepts with similar semantic meanings are located numerically close together. The more dimensions, the more nuanced the meaning that can be captured. How do we turn words, sentences, entire documents, images, or even audio clips into these meaningful numerical coordinates? That's where embedding models come in, often powered by sophisticated neural networks. These models are trained on massive datasets and learn to convert raw data into numerical lists, or vectors. For instance, the abstract of a research paper isn't just a string of words anymore. It becomes a unique vector, representing its entire semantic meaning. The magic is that if two papers are about similar topics, or two images depict similar objects, their corresponding vectors will be numerically close to each other in this high-dimensional space, reflecting their shared meaning. Once we have these vectors, we need a place to store them and, more importantly, quickly find others that are similar. This is where specialized vector databases shine. Unlike traditional databases that store rows and columns of structured data, vector databases are engineered and optimized specifically for lightning-fast similarity searches. They allow AI applications to efficiently query, "Find me all the vectors that are semantically similar to this one." Imagine trying to find all nearby locations on a map if you didn't have GPS, or a highly optimized search function. It would be practically impossible. Vector databases provide that super-efficient GPS for AI's conceptual map of meaning. Companies like Qdrant, Pinecone, and Weaviate are leading the way in building these cutting-edge solutions, pushing the boundaries of what's possible. So how does this all translate into truly powerful AI applications that feel smart and helpful? One major breakthrough is Retrieval Augmented Generation, or RAG. Are you tired of getting generic responses from a chatbot, or seeing it hallucinate incorrect facts? RAG dramatically improves AI by allowing you to provide relevant, specific context to your AI model. When you ask a question, the AI first uses your query to perform a similarity search in a vector database. It finds the most relevant pieces of information, like documents, articles, or notes, that have similar semantic meaning to your question. It then feeds this retrieved context to a large language model, enabling it to generate far more accurate, informed, and specific answers. This is how you can build a chatbot that not only provides rich, meaningful responses, but can also cite its sources, as demonstrated by the ability to build a chatbot with RAG in 10 minutes. The applications go far beyond just better chatbots. Think about semantic search. Instead of searching for exact keywords like hiking boots, you can search for meaning, asking for footwear suitable for mountain trails. The system understands the underlying concepts and provides relevant results, even if those exact words aren't present. This also enables you to build a second brain for your documents and ideas in minutes. By embedding all your notes, articles, research papers, and even audio transcripts as vectors, you can instantly find related information, connect disparate thoughts, and truly supercharge your personal knowledge base. No more struggling with frustrating keyword searches that miss the point, or trying to remember where you saved that one crucial piece of information. Integrating all these components, your AI model, the embedding process, and the vector database, can sound complex. This is where powerful frameworks like LangChain come in. LangChain simplifies building complex AI applications by providing a cohesive framework to easily connect various components, including different vector databases and embedding models, abstracting away much of the underlying complexity, as seen in LangChain Explained in 10 minutes. And while dedicated vector databases like Pinecone and Weaviate offer incredible performance and scale, specialized vector databases aren't always necessary for every use case. For smaller projects, or when working with existing infrastructure, you can even leverage traditional relational databases like PostgreSQL with powerful extensions like pgvector to store and query your embeddings, offering a flexible path for adoption, as demonstrated in Semantic Search with Llama and PostgreSQL in 10 minutes. Now, you might have heard of graph databases and wonder how they're different from vector databases. While both deal with connections and relationships, they serve distinct purposes. Graph databases focus on explicit, defined relationships between entities, like Alice is friends with Bob, Paris is the capital of France, or product A is a component of product B. They're excellent for understanding network structures and direct links. Vector databases, on the other hand, focus on the semantic meaning and times similarity times of data. They group concepts that are conceptually close, even if they don't have a direct, explicit link. Think of it as knowing what times things mean and how semantically similar they are, versus how times things are explicitly connected to each other. So the next time you interact with a smart AI, remember the powerful, hidden world of vectors and vector databases. They are the invisible engines powering AI's ability to remember context, truly understand meaning, and provide genuinely intelligent and nuanced responses. From building your own personalized second brain to creating incredibly insightful and accurate chatbots that go beyond generic replies, vectors are absolutely fundamental to the future of artificial intelligence. As AI continues to evolve and become more integrated into our lives, understanding and leveraging these maps of meaning will only become more vital for innovation and progress. The future of AI's memory is now. Thanks for watching. Don't forget to subscribe and share. See you later. Be awesome.
I hope that was insightful. Thank you for watching. Don't forget to like, subscribe, and share. Be awesome.